Example number 3, the 2D Laplace equation, steady state flow. So the problem here is solve the Laplace equation on the square domain. So our x here is from 0 to 1, y is from 0 to 1. So we have the Laplace equation here. So the boundary conditions that x equal to 0, so u is equal to 0. If x equal to 1, then our u is also equal to 0. So this is the left and right walls at 0. So at y equal to 0, the bottom left at 0 here, so that u is also equal to 0. At y equal to 1 here, so this is sine of pi x, top wall heated in a sinusoidal pattern. So we have the boundary conditions here. At the top wall heated in a sinusoidal pattern here. So x and y here is equal to 1. So u is equal to sine pi x equal to 0. So Galerkin approach choose trial functions that satisfies the homogeneous boundary 0 on the left, right, and bottom. So the pi here as a function of x and y equal to sine in pi x, hyperbolic sine of in pi y. But since the top boundary is not 0, we need a particular solution. Let's use one trial functions. This one. So at x equal to 0 here and x equal to 1, the sine pi x here equal to 0. So u is equal to 0. So at y equal to 0, hyperbolic of sine 0 equal to 0. So sine, so u is equal to 0 here. At y equal to 1, u equal to c sub 1 sine pi x, hyperbolic sine pi. So we force this to match the top conditions. So we have the residual and Galerkin conditions. So we have the Laplacian equal to 0 here. So wait, that's exactly 0. So this function is already a harmonic functions. An exact solution to Laplace equation. So the residual inside the domain is 0. The only error is on the top boundary, y equal to 1, where we have the boundary here is u of x1 minus sine pi x equal to these expressions. So we have the given residual functions here, c1 sine pi, and multiplied by hyperbolic sine pi minus sine pi x. Now we applied the Galerkin condition on the boundary value. This is called the boundary Galerkin or least square boundary approach. So we have the product of the R here, the residual functions, and multiplied by sine pi x, the x here. So the sine pi x dx here, sine pi x comes from this one. So this is the exact value, the exact expression for the functions. So we have by substitution here. So R here is equal to this times sine pi x equal to 0. So by simplifying this one, so we have the square of sine pi x dx, integral from 0 to 1, and this one also integral from 0 to 1 of negative sine square of sine pi x dx equal to 0. So we have the value of this expression, integral of from 0 to 1 of sine square pi x dx equal to 1 half. So by substitution here, we have c1 equal to 1 over hyperbolic sine pi. So we have the final solution here by substitution. Sine pi x, hyperbolic sine pi y over sine hyperbolic sine pi y. So this is actually the exact solution for this problem. It's a classic separation of variable solutions. The Galerkin method is perfectly uh, because our chosen child function was the exact again function of the operator. So we have the mathematical code here. We have the Laplacian trial functions. We have the Galerkin solutions here. This one. So value at the top boundary here, y equal to 1, u as function of x and 1 here. So this one. So we have the steady state temperature distribution Galerkin. So the steady state solutions using the Galerkin solution here. So the Galerkin solution here is the same as the original solution here as the exact solution. So this is actually the exact solution for this problem. It's a classic separation of variable solutions.